Okay, so I'm about to disable the QR code for the attendance. 6 out of 32. So can you see my slide?
Yes, Toto, yes, boleh.
Okay. Okay, last time where we left. Okay. So during our last class, what we take a look on, we already in the vehicle right topic, and last part that we add is actually the source of excitation that might affect the vehicle right comfort, which is what the the source of excitation might came from the road, it might came from your engine, it might came from your transmission, and also it might came from your wind, which is what we call as noise, noise, vibration, and harshness. But for this vehicle dynamic subject, we're just going to take a look or focus on the source which of excitation which came from the road, and how we're going to exclude that source of excitation from reaching the passenger inside the vehicle cabin, okay, passenger cabin. Okay, now we're going to take a look at the basic ride dynamics, which is we're going to a basic principle of isolation, and then we're going to take a look at vehicle ride modeling. In this topic, we not only covers on the quarter car model, we're going to take a look at the quarter car, half car model, and full car model. One second. Okay. So we're going to add for basic principle of isolation, and then we're going to take a look at the so half car dan full car model. Okay, and then just that for ride rate, we're going to take a look at the concept of ride rate using a quarter car model. We're just going to use example of quarter car model to roughly determine the ride rate, which is the rough estimation on how good our suspension is in terms of isolating unwanted vibrations which came from the road. And then we're also going to take a look at the suspension natural frequency, suspension natural frequency. So basically, a principle of isolation is that in suspension, one of the suspension function other than what holding the chassis is also absorb shocks from the road. Okay, the main function of the suspension system. Other than that function, the suspension function is actually to hold the steering linkages for the front axle, and then as well as all maintaining tire contact with the ground at all time, because in for vehicle it's very important for us to ensure with the tires always in grip with the road surface. If not, we're going to have an accident, even though that the tire is actually in contact with the road. We need to make sure that there is enough frictions. If not, we can, if there's no or lack of frictions, means that we're going to have a slippery road surface, and slippery road surface is not good for vehicle traction. And yeah, worse, it's going to cause accidents because drivers might lose control over the vehicle. Okay. Okay, now is okay. This is a basic illustration of the basic principle of isolation for suspension. So last time you did learn during your dynamic subject, you only learn about what mass spring system, which is just an introduction for you on how the motion of mass, which is being supported by spring, uh, 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 can be controlled in terms of the motion by using different values of spring stiffness and damping coefficient, which is from the shock absorber or damper. But that one only 1 degree of freedom, and that one we are referring to the application in terms of macam apa engine mounting. Okay, macam engine that in the engine compartment we have the engine being supported by the engine mounting. Okay, that is an example of a spring mass system. But for the vehicle suspension system, we actually have 2 degree of freedom, which is we have the motion of okay, yang for the spring mass system, using the example of engine inside the car's engine compartment, allowed to move up and down. Okay, that one is actually 1 degree of freedom. Okay, and then the basic engine mounting. But nowadays we have different types of engine mounting. It not only allows the engine to move up and down, but it also allows the engine to move sideways, like in the lateral direction. So that one is we're going to talk a different topic. But the most basic engine vibration acceleration for engine is just 1 degree of freedom, which is representing the mass and spring system. Okay, that is for engine. But for vehicle suspension system, we have like I told you, we have 3 ways in order to evaluate the vehicle ride comfort performance using the simulation model. And then this simulation model, we have either we can use the quarter car model, we can or we use the half car model, or we use a full car model. Okay, so this one is just equations. I'm sure that yeah, this is just most a typical equation that you can find in the literature paper. But but the most important thing for you to understand about ride comfort is actually to know how this equation being derived. Because later on in for this subject, you're going to have a project which you're going to model ride comfort performance of a vehicle. Um, okay, ride comfort performance of a vehicle using using this equation of motions, and then you need to create the interface to control that. So basically, the project is similar with your senior past semester. During past semester, I'm sure some of you might already kept or asked their model, but usually for each semester, I'm going to make it different. Okay, for last semester, it's just normal passenger vehicle. For this semester, I'm going to I'm going to start introducing to you on advanced suspension system, on how this advanced suspension system could further improve the vibration acceleration. So meaning that for a normal vehicle with conventional suspension, when you hit the bump, so you can see a spike of what of response. So, but at certain limit, at certain range. So when you install this main active suspension system, hitting the same bump, you're going to have the spike, but the spike is going to be lesser than the original one, or from the conventional suspension system. So this is roughly your project for this semester. Okay. Okay, back to this one. So we have right modeling. So let me put over here. So we have right. So you need to know we have three right model. First, uh, uh, quarter car model. Then we have half car model. Then we have full car model. The ones you know is actually the quarter car model. Okay. So okay, now I'm going to start for the derivation for the quarter car model. Any question? before I proceed with the equations of motion for the suspension system. Okay, this is one. Okay, this is the quarter model. So yeah, basically I'm just going to explain this note first. Okay, this is actually the example of a quarter model where in quarter model we only model only quarter mass of the vehicle, which means that we only consider only quarter of the vehicle, only one corner of the vehicle, where we took the mass of the sprung mass, and then we took the mass of the unsprung mass for that corner, and then we model in this simplified way, because in actual suspension system, the shock absorber and the spring is actually not in straight formation. It's actually we have a certain angle, which is the camber angle. But for the purpose of simplification, for mathematical modeling, we make it straight. Okay, so this is how we draw it. And then in this diagram, we take a look at, we can see that the most of the signs pointing downward with the input is actually came from the or being subjected to the sprung mass. So there are different versions of Kotka modeling. If you take a look in literature review or technical papers studying about the advanced suspension system, some of the diagram of this for this Kotka model, some of it being pointing the sign, pointing the signal or the input goes from bottom up, and for this one is going from top down. So it depends. So however, this kind of signage going to affect the notation of signs use the equations. Okay, but for this one, I'm going to, for this note just pointing downwards. Okay, but for derivation, I'm going to use the sign or the inputs going moving from bottom up. Okay, so boleh nampak tapi slide.
Boleh sir, boleh.
Okay, saya cukup takut bila saya tengah cakap tiba-tiba dia disconnected without me realizing, so saya kena tanya awak lah. Takut kau tak dengar. Okay, ni. Yeah. Okay. Okay. Just a moment. Just a moment. Okay. We're not in entire dynamic yet. Okay, for Kotka model, I think last time during your AD1, most of you already took the simulating class with me, right?
Yes, Doctor.
Masa
Yes.
dalam tu saya ada bagi tak Kotka model suspension example? Saya tak ingat lah. Ada ke tak ada? Did I give you the example of Kotka suspension modeling using Simulink during the AD1 class for you to learn the Simulink modeling? Ada punya tak? So saya assume tak adalah, saya pun tak ingat. Okay. Okay, so for Kotka model, so please record somebody, so saya tak akan record saya punya ni, so it's your responsibility to record the session. Okay. for a cortical model, first thing that we need to do is that we need to draw the 2 degree of freedom of vehicle suspension system. So we have the sprung mass, we have the spring, and then we have this damping element. And then as for the tire, we model the tire as a spring. So this is our road profile. So in this cortical model, so I'm going to use the sign, meaning that the input came from the road. So we're going to derive as if the input going to move from bottom up. So we have ZR. Okay. Then for this one, we have uh, ZU. So this one is a unsprung mass. This one is sprung mass. For ZU, in terms of its motion, we have the ZU double dot, or what we call as the unsprung mass acceleration. And then we have the unsprung mass velocity, and we have the unsprung mass displacement. And same goes for the what the sprung mass. We have the sprung mass acceleration. We have the sprung mass velocity dot, and we have the sprung mass displacement. Okay. Okay, now okay, so with MS, with MS equal to MS MU from MS. Okay, we have ZU and ZS. Kita ada apa? Kita akan simplify lah. ZU, ZS, ZU dot, and ZS, and ZU is from my function. And ZU and we have ZS double dot, ZS dot, and ZS is actually sprung mass motion. When I say sprung mass motion, we're referring to the acceleration, velocity, and displacement respectively. Okay, now it's time for us to derive the equation of motion for this okay. Okay, for now we take a look at the the equation of motion for the sprung mass. So we just need to draw the sprung mass, where at the sprung mass there's only two type of forces over here, which is oh no, I forgot. KS, PS, and KP. Okay, so over here we have at the sprung mass, we have FS and FD. Okay, based on summation of motion, summation forces S equal to MA, we have Fs plus FD equal to MS ZS double dot. So this is our first general equation. Okay, and then if you wonder, because based on free body diagram, typically there's going to be effect of gravitational effect where there's supposed to be mg effect pointing downwards. Okay, so let me show you. Okay, there's supposed to be an effect of mg. Okay, mg, but this mg effect we're going to neglect it because later on we're going to do a simulation. So in the simulation, the input starts with zero. So in simulation, when the inputs start with zero, this mg is actually a constant. So we need to eliminate this mg term from the beginning, because if not, we're going to always have our response in negative. And then later on, we need to offset that graph, and that offset value is actually equivalent to mg value. So yeah, later rather than eliminating this value at the end, so we're just going to eliminate this mg value from the beginning. So that's why we won't have any mg terms in our equation. Okay, understand lah? Jadi jangan cakap kalau salah, cuba diagram ni salah pula. Kita assume memang tak ada. Okay, this is actually the first general equation. Okay. Okay, so for unsprung mass, which is the mu, we have the suspension forces, but since that for the sprung mass, we have the suspension forces pointing upward. So when we are actually separating two bodies, the other body should have the opposite direction of that or initial sign that we use. Previously, for the sprung mass, we use the sign for suspension forces of Fs and Fd pointing upwards. So for the unsprung mass, we need to show that the forces of Fs and Fd pointing downwards. Okay. So for spring force or the tire force, we're going to show that it's pointing upwards. Okay, same thing. So we just need to show summation of forces. Same thing for this unsprung mass. We're going to neglect the effect of gravity. So we have Fs plus, oops, we have Ft for the, we have Ft tire force minus Fs minus Fs minus Fd equal to M U Z U double dot. Okay, so basically this is our the most the second general equation. Okay, now we already have the equation for the sprung mass and we have the equation for the unsprung mass. It's time for us to define what is Ft, what is Fs, and what is Fd. So Fs is actually the spring force, so being defined as Ks. So it's actually the spring equation is actually being given by spring stiffness multiply with the displacement. But in this case, the displacement is actually the motion or relative displacement between the sprung mass and unsprung mass. So we're going to use ZU minus ZS. And for FD, which is the damping force, is actually a product of damping coefficient multiplied with the relative velocity between the sprung mass and unsprung mass. So we have ZU dot minus ZS dot. Okay, and then for tire force, we have FT, which is product of tire stiffness or TT multiplied with the ZR minus ZU. So this is the fifth equation. This is the third, and then this is the fourth. Okay, now from this equation, we're going to create the Simulink model. Okay, so we use the parameter for MS is actually 250 kilogram, MU equal to 50 kilogram, KS equal to 17,900, um, Newton per meter. Okay, for CS we use damping coefficient as 1,500 Newton second per meter. For KP we use 179,000 Newton per meter. So using this parameter value to develop uh, Kotka model inside the Simulink. So we have, and then before that, for ZR, we use the amplitude. For ZR, it's actually 0.075 meter or 7.5 cm lah. So we're going to simulate that this Kotka model is going to hit bump of 7.5 meter centimeter or in terms of its height. So any question on this mathematical equation for the Kotka? I'm going before I proceed with the modeling in Simulink. Any question? Any question?
No, doctor.
Okay. So please wait for a while for my lab to open. Okay, saya nak share saya punya Simulink file. So ini faham this equation?
Paham doktor.
Okay. So boleh nampak saya punya Simulink sekarang?
Boleh doktor.
Okay, kita goes usually for Simulink for you yang nak revise balik how to model with Simulink because I already taught you briefly on how to do Simulink modeling during your ID1. So for this one, it's just going to be a revision as well as showing you the advanced what features for Simulink that we can use to model your mathematical behavior of the putting this mathematical equation into simulation model using Simulink is basically to start with the most general equation, and then from there we're going to narrow down. Okay. Okay, and then another thing is that in modeling the mathematical equations in Simulink, you also need to know how the equations be derived, or at least if you do not know how it's being derived, you need to know what the equations mean because you need to know in that equation what are the inputs and what are the outputs that you want to see. Okay, because it's going to affect on how you're going to rearrange the equation. Okay, but for this one, for quarter car model, half car model, and full car model, yeah, we already clear what we want to see, which is we want to see the input is going to be the root input, and then the output going to be the what motions of the sprung mass and unsprung mass. Okay, but for this one, we're going to start with the most general equation first, which is the equation number one and equation number two, which are the equation for the sprung mass and equation for unsprung mass. Okay, so okay, let's start. Pull out some log that we typically use. But again, okay, then some of integrator, then some. Okay, back in our slide. Okay, in Simulink for the first equation, okay, I'm going to show you for Simulink modeling for the first equation. We have Simulink. Okay, for the first equation, we have the Simulink example. So we're going to start with the first equation first, where we have the Fs plus Fd equal to M S Z S double dot. Okay. Okay. The way that we model mathematical equations in the Simulink is that we need to know that the signals actually works or move from left to the right. So meaning that your left side is going to be your inputs, which is going to go through some of what manipulation plus minus multiplied by gain or whatsoever, and in the end, on the right side is going to be your output. So you need to arrange this equation in the same manner. So if you are a beginner, so you need to write down this equation because, and if you are already familiar with it, you can do it in your head. Okay, but for this one, yeah, we're going to have the Fs plus Fd divided by Ms, and with the S, the dot is going to be our output. Okay, so the Simulink block will need to be arranged in the same manner like this equation. Okay, so tadi saya cakap buat apa? Alamak, betul juga. Ini, we have EFS plus FD equal to MS ZS double dot. So it's also the same as FS plus FD divided by MS ZS double dot. Okay. So in the way that we want to use in Simulink, it's going to be like this, the arrangement. Okay, we start with gain. This one is 1 over S. That goes into this 1 over S is actually the product of the spring force and damping force. So this one has the both having a plus sign. So we need to label this Fs, Fs and Fd. So we just let it hang first. Yeah, because this is still in general term for this equation one. We're going to come back to this one to further define what is Fs and what is Fd. So based on this one, we're going to get the Zs double dot. Okay, this is Zs double dot. So the output of the signal line over here is actually already be considered as Zs double dot. But I told you before, for vertical for the sprung mass motion, we're not only going to take a look at the acceleration, we're also going to take a look at the velocity as well as the displacement. So in Simulink, these values of Zs double dot, we can convert change it into the velocity by having integrator. Okay, like the what Kamiran in calculus, but in Simulink, that integrator we use the block is known as a 1 over S. 1 over S. We do single in to get Z dot, and then we do another one integrator, and we're going to get ZS. Okay, for the moment, for the first equation, so we just let it hang like that because we haven't completed yet. So in terms of application in Simulink, we can do like this. 1 over MS. So any parameters name that you haven't defined its value, you're going to label in red. Okay, so I'm going to highlight for you so the parent can keep or key in the values later on in the main MATLAB interface. So we're going to use sum, change this block to rectangle. So plus plus. So just so it's a good practice for you to label the signal line for you to identify, because this is still what a simple model. So yeah, when you have a complicated mathematical equation, you need to model the signal line. If not, you're going to get confused whenever there is error. And you need to do troubleshooting. So if you don't label your signal line, then you're going to get confused with the hair wire inside. Okay, so the output over here is actually ZS double dot. Another one. So we have ZS. That's dot. Then we have now done doing the equation for the first one. So now it's time for us to do the equation for the second equation. This one. Okay, this is the first question of our strong mass. Now we're going to take a look at the second equation. We're going to convert that equation into the simulant block. So we know that the equation is Ft minus Fs minus Ft equal to mu Zu double dot. So like I told you, what we want to see is actually the motion of the Armstrong mass. So we need to move the mu to the left or to the left side. So the term going to be the Ft to Fs minus Fd minus mu. Then maybe the hold on. Maybe Zu double dot. So the way that we're going to arrange these mathematical equations is going to be like this. We have mu with it being multiplied with the product of um, Ft, Fs, and Fd. Okay, so this one is going to be your Ft, this one is going to be your Fs, and this one is going to be your Fd. Then with the output is your Zu double dot, and then we do the single integrator to get the velocity of the Armstrong mass, and then we do another one of integration to get the Zu. Okay, now we're going to rearrange this in the block following this this rough sketch of diagram. Okay. So I can actually copy and paste the whole block and then just do some minor modification on this one. But for the purpose of this example, I'm going to build everything what that you. Mhm. Dot, dot, and this one is you. I'm going to use a negative sign because I want to pull out the signal line from upper side. So we're going to pull the FS over here, and we're going to pull the FD over here. So this one is your FD. Okay, now we're done defining the blocks for the first equation and the second equation. Now it's time for us to define the FS, FD, and FT. Okay, so the FS is actually uh, Ks multiplied by relative displacement between sprung mass, between the unsprung mass and sprung mass. So what we can do is that put again. So we have Ks, some block. So you need to be what? Plus and minus. Plus is sign for the unsprung mass displacement and negative sign for the sprung mass displacement. So we just need to pull the signal do the same thing for the ZX. Okay, now do the same thing for the FD. So for FD you have DCS. This one we have velocity, so just pull out the velocity information from the velocity signal line, which is this one we need the ZU ZU dot minus the ZS dot. Okay, then okay, now it's time for the KT. So for KT we have KT. So same thing, just rearranging the position of ZR so that you're going to look nice in this signal line. We put the positive first, followed by the negative sign. So okay, for the negative is actually ZR minus ZU. You're going to simply pull over here. And then for ZR is actually the constant input that we're going to give. For this one, we're just going to use a step input process from here. Okay. Step time, let's say 1. Final value is 0.075. Okay, done. So now we just put our scope. Now, mainly we're going to take a look at the displacement. So meaning that if the shock from the road being isolated by the suspension system, meaning that the sprung mass will not isolate the same way that the road did. Usually, the motion will be absorbed by the shock absorber, and we should expect that the sprung mass is actually oscillating at the lower amplitude. So let's say for this case, we're having a bump of we're having a bump of 75.5 cm. So when the quadcom model hit the bump, so we should expect that displacement of the sprung mass is going to be less than lesser than 7.5 cm. For example, it can be 0.1 cm, or it can be 1 cm, it can be 2 cm, but always less than 7.5 cm, which is lesser than our road input amplitude. So I'm going to put the input. Okay, over here. So we have the KS to 7,900. S equal to 1,500, KT equal to 9,000, MS equal to 250, MU equal to 50. So here we already put it inside the block. So yeah, we're going to set the simulation time up to only 3.5 seconds, because for 10 seconds it's going to make your graph look small, because after usually for this kind of estimation of after 2 seconds, 1 second something, it's just going to have a straight line of zero. So we're going to shorten the estimation time to get to maximize the curve. So next we're going to change the sampling time. Okay, so it needs change to fix that. We have a uniform sampling. We use 0.01. Try to run it for the first time. Usually for the first running, we uh, try run it to make sure that there is no error. And then when there is no error, then we proceed checking our result. So we need to that, but give you a wrong answer, or it's just going to give you unstable results. So you need to check that. For this one, is that our input is actually in the form of step input, like this one. So we should expect our graph also to be in the form, generally to be the way in the same form as like the step input. This one is mentioned. Dia tak ada, kita tengok result lah. Ya, ada error lagi kat sini. Apa? Okay, dia ada error kat sini lah. So, okay, kalau ada error kat sini, kita akan check lah dia punya sign. In this case, KT. Set ni. Saya pakai variable tengok. Ada error tak? Okay, kalau macam ni kan, yang tadi saya cakap, walaupun tak ada error, sepatutnya kita tak patut dapat this kind of result. Dia macam tak settle down. Okay, dia sepatutnya dia lepas hilang gebam je, dia sepatutnya settle at that bump lah. So but in this case it's just going towards infinity, which is not true lah, walaupun kita punya simulation tak ada error. So we need to find or figure out why. Okay, let me check ini, takut ada saya salah sign ni. Yes,
Yang dekat tire force tu salah tu.
yeah.
Yang subtraction.
Yang mana?
Kan ada ZR minus ZU tu. Salah tarik. ZU double dot tu doktor salah tarik.
Yeah, okay, thank you. So ini salah. Okay, so okay, thank you. Yalah, kan tu saya cakap. So kalau kita ada ni senang lah, kalau kita dah label ni, so kita boleh identify. Sekarang tu lagi. Ini baru betul. Okay. Betul lah ni. So kita ada kita ada set input. So bila dia langgar bump, usually bila kita langgar bump tu kita itu akan apa? Oscillate lah, akan terhenjut. So kalau dia dah henjut tu dia akan settle down lah, because in our suspension system we have damping or damper element or shock absorber. So that damper, one of the main function is actually to control excessive motion of spring. Sebab kalau tak ada damper, kita akan keep on continuing oscillating. Okay? Contohnya kalau saya pakai dalam ini, saya tak ada, katakanlah saya buat CS equal to 0. So kita boleh nampak lah dia punya macam ni. Okay? Dia akan keep on oscillating. Okay? So okay, this is what you learn during your dynamic subject spring mass system. Okay, you have a damping coefficient. So you have the value for epsilon, because epsilon value is going to determine either your suspension or spring mass system going to have underdamped oscillation or apa damped oscillation or overdamped oscillation. So itu samalah in this case. Cumanya dalam ni kita play around the value of TS in our suspension system. Jadi so ini saya tukar balik. Tak ada error, saya tukar lah. So, buat saya nak impose these two result, saya buat 2. Sekarang tarik tutup. So, macam ni. So meaning that this is our bump height. So for the suspension system, for this front mass, when you hit the bump, you're going to oscillate like this. For in this case, kita akan ada overshoot sikit lah. Okay. Jadi kalau macam yang saya cakap tadi, yang kalau kurang daripada bump height ni, kalau kita pakai advanced suspension system, either kita pakai semi active suspension or active. Okay, itu kalau macam kita punya bump height ni 0.08, 0.075, kadang-kadang dia takkan ada overshoot. Dia kadang-kadang dia tak ada overshoot, dia terus boleh settle down kat sini. And then that kind of behavior, so we can maintain at any kind of speed, any kind of input. Okay. But for this one, kalau nak rendahkan boleh je. So kita just play around with damping, the damping value. But kalau kita rendahkan damping value, we can have a softer suspension system, which is good for shock absorption, but not good for handling. Itu macam yang saya cakap lah, for in right handling, kena ada compromise lah between right handling. Okay, tapi ini only for conventional suspension system, which is using normal spring and normal shock absorber. Tapi kalau kita pakai advanced suspension system, for advanced suspension system, kita boleh ada soft suspension system, soft suspension setting, which is going to give us good comfort masa langgar any kind of road harshness. Tapi bila kita bawa laju, in terms of masuk corner, that suspension can change behavior or characteristic from soft to hard. Okay, itu advanced suspension system. Itu nanti lah saya akan tunjuk. Okay, so ada apa-apa soalan ni mengenai ni? Ada? Ada soalan untuk kau?
Tak ada, Doktor.
Okay, now kalau tak ada, saya nak tunjuk sebab kita on the same example. So saya akan tunjuk example for signal management. So kalau awak tengok sini, our model is actually a bit haywire. Okay, kalau ini just only involve 5 equations. Later on when we're going to take a look at the half car model, full car model. For example, for half car model, we're going to have berapa equation? Ada ada 4 degree of freedom for general equation, and then we have 2, 6, we have 10 equation of motion for half car model. But for full car model, we have about 20 equation something. So when we put more model inside this Simulink, it's going to look haywire. Okay, kalau ada error macam tadi kan, tadi saya tengok pun Ini pun saya dah mata berpinauan, saya tak nampak sebab saya dah pergi sambung kat ZU dot. Sepertinya kat ZU. Tapi kita boleh detect sebab dia simple lagi. Okay, kalau dia tak simple lah, kita cuba simplify lah. So, the way that we're going to do simplification through several ways. Either we can use go to tag. Contoh saya buat signal routing, kita pakai go to tag from go to bus filter and bus selector. Ini saya tak boleh, saya akan pakai dua ni lah, bus filter for proper signal management. Ini saya tak letak lagi lah dalam ni. Kalau letak ni tak ada input ni, dia akan bagi error. Okay, so saya tunjuk dulu. So sekarang ni kita ada yang ni, this one. Okay, saya akan buang sebab ini kita nampak hairwire sebab kita perlu tarik signal daripada ZU velocity and displacement for each sprung mesh and non-sprung mesh kan. So the way we're going to simplify is that kita akan letak di, go to tag. Okay, so ini saya akan delete balik yang mana yang signal yang saya tarik tu saya akan delete. Yang mana ada saya akan buang. Okay, so yang ni saya nak bagi signal ni clear je. Ini saya label ni as access. Ini sama juga saya tak nak ni. So ini kita letak so make sure you label lah dia punya map ni. So ini kita letak that S Z U and Z S dot this one we have ZU. So now for each of this red signal line kita letaklah go to tag. So apa yang kita nak ada ZS, kita nak ZU, kita letaklah kat sini. So make sure awak double click this one, change the go to as a ZS. Awak kena tukar nama dia satu-satu. And then awak make sure tag visibility ni always global. So nanti bila awak nak buat nak kemaskan lagi pakai folder buat mask ataupun nak create folder for this one. So the signal line, the signal can go up from that mask or folder. Okay, so nanti saya akan tunjuk lah apa maksud saya ni. Yang saya pakai folder ataupun mask. So for the moment, for every go to thread, awak kena namakan and then awak kena change tag visibility to global. Okay, then buat the same thing for ZU. Okay, we do the same thing for ZF dot. Then we do the same thing for ZU dot. Nak tarik je lah. So kita perlukan ZF kat sini, kita tarik je. So ni ada biru kan. Awak klik sini, awak tarik je. So ataupun awak boleh buat manually lah. Awak ambil kat sini, awak type. Awak tarik daripada library browser. Awak double click, awak tekan nama. Tapi shortcut dia awak tarik drag daripada go to block. Go to form. Sebenarnya ni ZF. So awak perlukan ZU, awak tarik je. Daripada dekat yang dia pun. Kalau buat macam ni awak, you don't have to type di from JS dot, so just tarik je keluar. Just simple for ZU. For ZU. Now we need the FS and FD. So yang FS tadi you can simply pull tarik dia punya signal lah, tapi ya kalau nak demo saya tunjuk sama juga, can simply pull the signal line from here or use the go to tag. Ini saya buat FS. Okay dah. Dah kan? So nampak less haywire lah inside our block. Okay. So, kalau nak nice, okay. So ni, okay. Kita cuba run. Okay, tak ada error. Ini tak adalah. Kalau saya belum sambung dengan dia. Okay, same thing. Okay, ini saya setting lah. Saya kena keluar pedal line. Okay, now, okay, katakan kita nak, okay, usually in simulation model or control system, okay, the way that we, okay, usually bila kita buat simulation model, be it in conventional model or advanced model which comes with the control system, usually we're going to arrange the simulation or simulating blocks which represent phases of input, processing, and output. So it's a good practice to have this kind of block arrangement. If not, you're going to have haywire model, which is going to be look complicated. Okay, for this one, I'm going to show you that let's say that we want to have this one. Okay, katalah saya nak buat okay, saya nak buat this one. I'm going to look at the input. So this one is the input. We still need the process or the plant, and then we need to have the output. So for the plant, so we need to create a folder. We just need to select everything, right click, create a system. Then you're gonna have a simplified model, where you can see your what the blocks right in a folder. You just a sneak peek of it to disable this view if you want. Okay, now if you want to to display the result, so we can basically put at the okay. So we still have the JS, but we don't want to use that one. What we need to have is the output sources. We put the put this output port. So this one basically going to act as like a door out to go for the signal to go out from the folder or master subsystem. So this one is JS. Label it. Then put another one for the is this one. Okay, masuk, and then you're going to channel it back out. So go out. You already have two signals. One belongs to JS and one belongs to ZR. So just put the scope. Then okay. So you may see your result over here. Okay, this is actually one of a way of managing a Simulink in Simulink. Ensure that you have a tidy model or reducing the complexity of your Simulink block for your simulation model. Okay, and then this is another way. And then another way, if we want to use the bus creator or bus selector. So I'm just going to demonstrate to you. So we have this one. And then let's say that we just going to use server. Contohnya lah saya nak display semua result of yang kita pakai kat go to site tadi. Okay. We have JS. Ada 4 basically. 4. Ada JS. have ZU. Ataupun kita ada ZS dot. Okay, now this signal kita go to connect is must to have a bus selector and bus selector, because the function of bus selector is actually to what to select any desired input or signal that we want to observe or see. Kalau contoh sekarang ni kita ada 4 yang masuk dalam bus selector ni, tapi yang select kita kata nak tengok contohnya displacement saja. So we just pull out the displacement. So kita tengok this one. So just select so we just want to see the signal ZS only. So kita buka select. Okay, apply. Okay. And then one thing that you need to make sure that for each go to tag ni, you need to ensure that the signal line which is associated with the go to tag, you need to also to change the signal line, because yeah, it's actually the one that you're going to be used by this bus filter. Is that okay? You. Okay, then yeah, second one that want to see is actually ZU dot. Select. Okay. Move up. Okay. And have two graphs. Okay. But because the ZS displacement and velocity is actually two different parameters, so I cannot impose them these two signals together. So I'm going to change the layout. So let's say that I'm going to change it the graph in this way. So it's going to be laid in form of column. One belong to ZS, another one belong to ZS dot, another one is going to label this one. Okay, okay, this is the result. Okay, this for ZS. Okay, this for ZS dot, and then this one for ZU dot. Okay, let me disable this one. We add another one, which is the ZS double dot, which we still like. We need to reselect everything. So ZS. Okay. So kita select lah balik. ZS double dot select. So we want to take a look at the in terms of assertion first. Move up. Then one see in terms of ZS. So remove. Yeah. We just want to see motion of this farm. So assertion, velocity, and displacement. So ZS dot, select, and then the S is the last. Okay, next. We have three. Just layout to three. Okay, nampak So we have the first graph belongs to the vertical acceleration, and then the second one in terms of velocity, and the third one is actually in terms of displacement. Okay, any question? Any question for this one? For cortical modeling? Because yeah, you need to um, familiarize yourself with modeling because this is going to be your project. So quarter for half car modeling and full car modeling, we're going to cover it tomorrow morning, and then as well as we're going to have a replacement class on tomorrow night. Okay, any question?
No, doktor.
Okay, kalau tak ada, okay, ini saya dalam Okay, any question?
Doctor, how
Yes.
about the next one?
This one for this coming Saturday lah. So the content is going to be up to right topic, but only up to full car modeling, which is we're going to cover it tomorrow. Yeah, tomorrow.
Got any past year or question for us to do the practice?
Uh, got, but yeah, I'm going to share you the general question. But usually, the first test is just 1 hour and 15 minutes. Usually, it's not that hard. Okay, if you focus in my class, because it's not going to be um, uh, uh, test one test one material is just things that I only the lecture in class. Okay, not things that which is not uh, uh, outside from my presentation. Okay, so it's usually quite simple. If you do or focus on my lecture, they should be able to do it. Jadi saya tak tanya pelik-pelik lah. So kalau just you just read my note, the PowerPoint notes, it should be okay. Okay, there.
Okay, doctor. Thank you,
Okay,
doctor.
usually just going to involving if it is a calculation, it's just going to be involved simple calculation, and then if it's going to be in terms of definition, so you need to know about definition, things that I deliver in class only. Okay? Yang outside tu saya tak akan tanya. And then for derivations, yeah, things that I derive in class, then you need to study lah. So that one. So So that's usually for the content for test 1. Okay, yang mana dan usually things that yang saya tak tanya dalam test 1 tu akan keluar lah dalam final exam. Tapi yang walaupun saya dah tanya dalam final exam, kemungkinan akan keluar juga. So usually macam tu lah. Okay, so nanti saya akan tengok balik saya punya test. Past year punya test 1 punya question. Tapi ada punya answer script lah. So just need to read the example of the past year test and then try to figure out or discuss among yourself. Okay.
Okay, Doctor.
Okay. Any other question? So kalau tak ada, kita dismiss early today. So tomorrow class is at 9. So basically, yeah, at 9 we're going to continue with the modeling of half car model. And then for replacement class tomorrow night at 8:30 p.m. we're going to take a look on the full car modeling. Okay. So if not, okay, so we can dismiss. Okay, Assalamualaikum and good day.
Thank you, Doctor.
Okay, thank you.
Thank you, Doctor.